All right. So this week's speaker is Dr. Lizeth Magaña, who traveled down yesterday from Maryland, from the Johns Hopkins Applied Physics Lab, where she's currently a postdoc. She is a planetary scientist, and most of her research has focused on studying volatiles on the moon, mainly from observations, and I think also a little bit of modeling. I know she's done also experimental work, characterizing regolith, not only for the moon, but also for comets. Mm-hmm. And she has a bachelor's degree from Emporia State, which is in Kansas. Mm-hmm. And then she has a master's and PhD from the University of Texas at San Antonio. But I learned that she's actually from California, so she's been traveling around. And like I said, she's now a postdoc at APL. And so thank you so much again for coming down to visit, and the floor is yours. Thanks.
Sure. Thank you, Francis. Slight correction, actually, sorry. No longer a postdoc. So.
Oh, yeah. That's a good correction.
Yeah, it's as of a few months ago. So nice. Yeah, and then I'll also add I do a little bit of tie-in geomorphology. It's sort of a new field that's completely different to me that I'm trying to get into. But today I'm actually going to talk about condensed volatiles inside of permanently shaded regions. So you may know a little bit about this. I am transitioning to be the volatiles lead for LRO, so hence the multi-instrument view of these volatiles. So before I get started, one question is always, why do we care about volatiles? So they're important, one, from a scientific background, and that is we're interested to know the volatile history of the moon, how the volatiles got there, how they evolved. And second of all, they're important from a resource utilization perspective. So how can we access these volatiles to use them for future crewed missions to the South Pole? I think I accidentally went ahead and skipped the animation. So there's a variety of different ways that volatiles could get to the South Pole. There's three main ones. The first one is cometary and asteroid impacts. The second is outgassing from the moon's interior. So this is like volcanism. And the third one is from the solar wind. So you have hydrogen atoms from the solar wind coming in, interacting with the surface, and we can produce OH this way. And regardless of the routes that these volatiles take, once they enter the lunar environment, they sort of hop around along the surface or follow these ballistic trajectories. And most of them are honestly going to be lost to space, but there's a very small amount of them that could stick around, could make it to the South Pole or the North Pole. And this is interesting because at the poles, we have regions that are known as permanently shaded regions, or PSRs, as I'll keep referring to them. And inside of these PSRs, there's cold traps. So these PSRs do not receive any, or they receive very little direct solar illumination, which means that the areas inside of them can get really, really cold. So what I'm showing on the left is an annual maximum temperature map of the South Pole. So we have three major cold traps. These are Hayworth, Shoemaker, Bassini, right in the middle there. These are three of the largest cold traps. There's also Cabeus in the top left. This is also really interesting because in 2009, there was the L-Cross mission. This was an impactor that went to the moon. It impacted inside of Cabeus. When it did, it produced this plume. We're able to look at the plume with LRO and look at the volatile abundance within that plume. And so we saw things like water, CO2, SO2, NH3. So Cabeus is one place where we've actually been able to directly observe these volatiles. Now, there's also an unnamed cold trap just to the right of Hayworth on top of Shoemaker. This is one region that I always include in my studies. It's sometimes overlooked. It's unnamed. I've tried to name it. They don't want to name it. And then there's Nobile. That is where Viper is going to be roving around trying to ground truth some of these volatile observations. And then lastly, there's also Amundsen. And so that's on the far side over there. Amundsen is particularly interesting because it's really large. And so that means that there's an area of the crater floor that's permanently shadowed. And there's also a region of the floor that's always illuminated. So that's a really good test bed to look at some of these ideas of whether volatiles are there or not. And so these are really the 7 regions of interest that I'm going to keep referring to throughout the talk. And as I mentioned, this is a multi-instrument view of volatiles at the South Pole. So when LRO launched back in 2009, it had a payload of 6 different instruments. I'm showing maps from each of these instruments at the South Pole. They're on the right. We're going to focus on 4 of them. And rather than going into how each one of these instruments works right now, I'm just going to introduce them as they come up throughout the talk. But we're going to focus on LAMP, which is the UV instrument, Lyman Alpha Mapping Project. Diviner, which is a thermal radiometer. LOLA is a laser altimeter, and LROC, which is the visible camera. So using these instruments on board LRO, we found lots of evidence of condensed water at the South Pole and also the North Pole. There's also been studies by M-Cubed on board the Chandrayaan-1 spacecraft. And so the maps on the right here are a compilation of all of the individual pixels that have been found to be consistent with water ice at the North Pole on the left and the South Pole on the right. And the grayscale here is a temperature map. So the really dark areas, again, are the cold traps where water ice could be thermodynamically stable over billions of years. And what we're seeing is that these pixels that are consistent with water ice are truly constrained to these cold traps. And so, places where it's cold, there's water ice. We've also tried to constrain the abundance with different instruments. So with LAMP, we found somewhere between 0.1 to 2% water ice by mass. That's in the topmost, like 100 nanometers or so of the surface. M-Cubed found abundances as high as 30% within individual pixels. So that's not an average, that's just like certain very individual locations may have that much water ice. And as I mentioned with L-Cross, we found mostly water ice. We also found 6% NH3 relative to H2O, 3% SO2, and 2% CO2, and lots of other volatiles. So first up, Lyman Alpha Mapping Project, LAMP. As I mentioned, imaging UV spectrograph on the South Pole of the Moon. This instrument has a special place in my heart because it's the first instrument I worked with. So I started with LAMP in grad school. So as LRO orbits the moon, super cheesy animation here. LAMP is facing directly onto the surface. As I mentioned, PSRs, they don't get much sunlight. So we had to be really clever to develop a way to look inside of these PSRs. So instead of looking at sunlight, we look at reflected starlight. So UV bright stars and the interplanetary medium are the main illumination sources. So as you can imagine, background stars are very faint within these PSRs. So we have to accumulate data throughout years. So for these maps, I'm looking at the first 7 years of the mission. We also have to be very careful with our processing methods. So I won't get into those, but if you're interested, it's in that citation up there. And now LAMP has a wavelength range of about 60 nanometers to about 200 nanometers. We're really only interested in the wavelength range that I'm showing in this spectra on the right. So this is about 130 to 190 nanometers. And this is the far UV spectra of water ice. Now we see that it starts out pretty low, pretty dark. At about 165, there's this water absorption edge where the albedo starts increasing, and then it levels off at this higher level in about 180 or so. And so that's how we develop and decide what our wave bands of interest are going to be. On band is where the albedo is low. If there's water ice, low albedo. edge band is where we expect this water absorption edge to be, and the off band is where water ice would be extremely reflective. So then we develop an off band to on band ratio, and where this ratio is high, sort of makes into an intuitive sense looking at the spectra that it may be consistent with the presence of water ice. So high off to on band ratio becomes our proxy for water ice. The higher the ratio, the more water ice abundance. Now, in addition to producing those maps that I just showed you, we can also look at the spectra of these cold traps. So the blue spectra here are cold traps, the black are non-cold traps, so regions above 110 Kelvin where water ice would not be stable. And I'm looking at the average of 6 different regions of interest at in the top panel. That's Faustini, Shoemaker, Hayworth, Cabeus, the unnamed region, and Amundsen. And then the bottom spectra is the average of all South Pole cold traps, poleward of 85 degrees south, and then the average of all non-cold traps. And what we see by looking at these two spectra, first of all, is that they look pretty identical. They're remarkably similar. And what that tells us is that our 6 regions of interest that we're looking at are pretty representative of the average cold trap. Second of all, the other thing we notice is the shift in the y-axis. So the blue spectra is offset from the black spectra. It's about 13% darker. And this, spoiler alert, I'm gonna start talking about the modeling. We can model the spectra and we can find that this Y shift is completely explained by the porosity of the regolith within these cold traps. So if the porosity inside the cold traps is increased, we get this reduction in albedo across all wavelengths. And then lastly, we see this increasing off-band albedo. So if I can use the mouse, that is this increasing region here. Interesting is that we see it for the cold traps and also for the non-cold traps. So as I mentioned, this increasing albedo could be an indicator for water ice. So that's why it's interesting that we see it in both regions. So now we start to get into some spectral modeling. If we are seeing water ice within these cold traps, how much water ice are we seeing? So for this, we use Hackey's formulation. Plotting albedo as a function of its single scattering albedo and its porosity. And we use intimate mixtures of lunar regolith at 50 microns and water ice grains of 5 microns. And we're doing this for high porosity, that's the top panel, and low porosity, that's the bottom panel. And we are assuming that the regolith at the South Pole is similar to Apollo 10084. And so that is that gray curve there. That's 0% water ice, that's 100% 10084. Now the first curve that you see there, that first step, is 1% water ice mixed in with that regolith. And we see that even for 1% water ice, we can see an absorption edge. So even really small amounts of water create this signature that we can pick up on. And so then that steps 1%, 2%, et cetera, all the way up to 5. So for our actual modeling, we calculate the off to on band ratio at 0.1% weight steps. And then we compare those off to on band ratios with our observations that we saw from those maps. And we found that our observations are consistent with 1.4% H2O by mass, if we assume high regolith porosity within these cold traps, or 1.9% weight if we assume low porosity. And then, as I pointed out, we also see that increasing albedo outside of the cold traps, and we modeled that as well. And we found that that's consistent with less than 0.2% weight H2O. So then, our final step here is to compare with previous studies. So the first papers that looked at the South Pole cold traps was by Gladstone et al. In 2012. There is a follow-up study by Hain et al. 2015. So when we try to compare, it's actually a little tricky because the wave bands that they chose are different than the wave bands that we chose. So they had really wide wave bands because they only looked at the first 18 months of data from the mission because that's all that was available. So they had to, bin over much larger wavelengths. So if we make this adjustment, that's the purple X's there. We really only had a few regions of interest that were overlapping. So that's what's in this yellow box. But we find, fairly good comparisons. There's some differences, of course. One, due to the amount of data that we're looking at, and two, due to processing methods. But we still have greater than 40% agreement. So now we approach our second instrument that we're roping in. This is a diviner lunar radiometer experiment. I'm just going to call it diviner. It's the thermal radiometer of the moon. It observes the moon in the IR. And we've sort of already been using diviner. That's how we established what our cold traps were, regions colder than 110 Kelvin. And this is sort of where it comes from. So the lifetime of the volatiles at the South Pole are really going to be driven by their thermal stability. That is by their sublimation rates. And so on the right here is a map of the lunar South Pole. And it's showing areas where water ice is stable. So that's in blue, sulfurs in yellow, ammonia and organics are in the bottom panel. So we can use diviner to try to constrain what volatiles we think may be within these cold traps just by looking at areas where these volatiles are stable. So we use the stability temperatures to inform the likelihood of different volatiles. So when we model this out, we looked at the 5 most abundant volatiles that we saw with L-cross. That was H2S, NH3, CO2, SO2, and of course H2O. Now there's a few other loss mechanisms that could be eliminating our volatiles within the South Pole. I'm showing those there. It's slime and alpha, photodesorption, impact gardening. There's some ion sputtering as well. But the main one is really this thermal component. So what we do is we first establish a stability temperature, and this is somewhat arbitrary. It's the temperature at which 1 kilogram per meter squared of ice would survive for 1 billion years. It's sort of the convention that's been established in the literature. So for water ice, we find that this is 101 Kelvin. So areas at 100 Kelvin and colder, water ice is stable for 1 billion years. For SO2, it's 72 Kelvin, and H3 is 63. And then when you get to CO2, you start to see really low temperatures. You need temperatures of 52 Kelvin or colder. And for H2S, you need temperatures of 48 Kelvin or colder. And since I'm looking at areas where the maximum temperature is cold, there is maybe a pixel where the maximum temperature is colder than 48 Kelvin. Not enough to really do science with. So for that reason, I'm no longer going to look at H2S in the rest of the stock. The next question then becomes, what is the far UV spectral signature for these volatiles? So I'm showing H2O in blue. We've already seen the spectral signature of water ice in the far UV. It's a plot I showed earlier. And we see that this one actually looks different. This is laboratory data from Wagner et al. In 1987. And there's this weird high albedo in the on band in that grayed out region. We don't think this is true. So we just gray it out. We're not going to use it. Just ignore all the spectra at 140 or 158 and lower. So then we look at the red curve, CO2. It's very similar to H2O. Looking at the bottom panel, we look at NH3. It has a similar curve, not quite the same. It's low and then it increases in the off band. But SO2 is very different. It decreases, so the off band is a lower albedo than the on band. So if we're using our method of looking for high off to on band ratio, SO2 is not going to be detected in this way. So we have to eliminate it from our study as well. So in the rest of this talk, we're going to really focus on H2O, CO2, and NH3. So next, we just plot our albedo for each one of our wavebands for LAMP against temperature. And we get the plots that I'm showing here on the right. This is not what we expected. So we see this increasing trend with albedo and temperature. It's most prominent in the off band. We've tried to explain why this is, and we haven't really been able to explain it. So if you have ideas, let me know. But what we can say is that it's not increasing because of condensed volatiles. And we know that because, as I mentioned, water ice is not stable at temperatures of 200, 250, 300 Kelvin. It's going to just immediately sublimate away. So we normalize for that trend. And that gives us this normalized off-band to on-band ratio with temperature. And this is interesting because we see that at these colder temperatures, there's a 20% increase in this off to on-band ratio. And so it's, you know, a little, you can argue where that increase is. It's about 115 Kelvin. So in the realm of where water ice is stable for about 1 million years or so or more. But we also see that these increased signatures span temperatures where NH3 is stable and where CO2 is stable. So I've just marked those up here. So it's really hard to say whether these increased off to on-band signatures are due to water, or if they're due to NH3, or if they're due to CO2 at these really cold temperatures. So to try to disentangle this at least a little bit, we developed a normalized albedo difference. So that's the off to on-band ratio. We go back here, where only water ice is stable. So that's between 70 Kelvin and 115 Kelvin. Normalized to where water ice is not stable, which is 150 Kelvin and greater. And so that's what I'm showing in these black diamonds on the right-hand side. And then we do something similar for NH3. Of course, NH3 signatures also include water ice. And we do it again for CO2, and then CO2 includes NH3 and H2O. So it's still a little convoluted at the colder temperatures, but we at least can start to separate it out a little bit. So the NH3 signatures are the squares and the triangles are the CO2 signatures. And what this really gives us is a way to compare the relative abundance of these volatiles across different regions of interest. So for example, Faustini, Shoemaker, Hayworth, all seem to have about the same abundance of water ice as the average South Pole trap. For CO2, we see possibly higher abundance at Hayworth, the unnamed region, and Amundsen, and then for NH3, possibly greater abundance within Amundsen. So just to summarize here, because I've been talking for at least a little bit of time, we find lower albedos across all wavelengths within cold traps, consistent with increased regular porosity. Within these cold traps, we also find that they are consistent with 1.4% water ice by mass. We find that these signatures are really constrained to temperatures below about 115 Kelvin. And we were able to develop a method to provide insight on the relative volatile abundance across different regions of interest. Now, our third instrument, LOLA, Lunar Orbiter Laser Altimeter. So the way this works is LOLA emits a laser beam at 1064 nanometers. It hits the surface. They are able to measure the reflection back into the instrument. And this is how we develop digital elevation models of the surface. You can also use it to look at the albedo. So regions with higher reflectance within the PSRs may indicate water abundance. And this has been done by Fisher et al. In 2017. But more recently, it's been used to look at the roughness of the moon. And so that is the deviation from the mean topography. So you have a plane, how much it varies up or down is the roughness. So it's a quantification of how smooth the surface is. And this study by Deutsch et al. In 2020 found that the PSRs are smoother than the surrounding regions. And so they came to the conclusion that this may be due to terrain softening from these volatiles. Now, it could be softened due to volatiles, but there's also a variety of different mechanisms that could be taking place that could also decrease the roughness, and that includes mass wasting, so material coming down from high slopes, and that includes infilling from debris from like cratering that's going on nearby, infilling the crater. So we're going to look at all of these ideas, not just volatiles, and try to determine whether the softening is actually due to volatiles. So we look at the roughness across two different baselines, 50 meters and then also 30 to 120 meters. And yeah, this is the extent over which the deviations in the Z direction are calculated. And then lastly, before we really get started with this part of the talk, we are looking at roughness ratio. So it's not really appropriate to look at the roughness of one area and compare it to the roughness of the other area. So we're looking at the roughness relative to the immediately surrounding region. And that's how we're able to compare across different regions. So, of course, we go back to our 6 regions of interest, Faustini, Shoemaker, Hayworth across the top, Nobile, Cabeas, unnamed region across the bottom. Spoiler alert, we find the same thing as the previous studies. These cold traps are 7% smoother than the surrounding regions at both of these baselines. But we can't really look inside of them to figure out why they're smoother. But where we can look inside of are equatorial craters. So we find 6 equatorial craters that are as analogous to the South Pole craters as we can get. So we chose them based off of age. They're all pre-nectarian, just like our South Pole craters, meaning they're all older than like 4 billion years. We chose them based off of size. They're very similar diameters to the South Pole craters that we're looking at. Based off of composition, they're all highlands. There's no evidence of Maria inside of them. And based off of location, so they're at the equator, so we can use sunlight to look at them. And from this analysis, we found that these areas are 10% smoother than the surrounding region. So they're even smoother than the South Pole was. So why is that? So this is where we bring in LROC, the Lunar Reconnaissance Orbiter camera. It's a system of cameras, so it's 2 narrow angle cameras, 1 multispectral wide angle camera. And we look at the mosaics that are available on QuickMap. I don't know if you're familiar with QuickMap. It's a great tool to compare different data sets very easily. So I'm showing those 6 regions that we identified at the equator here on the right-hand side. First of all, we found evidence of light planes. That's what's outlined here in white. So that is debris from surrounding cratering that occurred. So it's like regional infill. We found, or we looked for impact melt, did not find impact melt. We found evidence of severe degradation at these craters. So we found uneven rims all around these craters. Some of them you couldn't even make out the rim. We found evidence of mass wasting. So we concluded that these areas are really smooth because of a combination of all these, the main one probably being regional and basin type infill and emplacement, but also everything else I just mentioned, degradation, mass wasting, etc. So even though we tried our best to find craters that were as analogous to the South Pole as we could, there really is differences between the South Pole and the equator. There's different amounts of infill that we can expect at these 2 locations. So instead we moved to Amundsen. As I mentioned, Amundsen has a permanently shaded area on the floor and an illuminated area. So this is a much better comparison that we can do. So we only look at areas where the slope is less than 10 degrees to try to eliminate that mass wasting effect. That's how we determine our PSR area of interest that I marked there with 1. Once we had this, I found an area of the illuminated floor that was of similar slopes and about the same distance from the crater wall as the PSR was. And that becomes our comparison point. Comparing these two, looking at that histogram down there, we found that the PSR was 35% smoother than the illuminated floor. That study by Deutsch et al. 2020 that I mentioned, they found about 30% differences. So this is within the same ballpark. And so lastly, I just threw everything together in a plot as well as I could. So trending roughness with temperature, sublimation rate, and off to on band ratio. We see, as we did before, regions where it's cold, we have higher off to on band ratio. We also see areas where it's cold, we have this decreased roughness that we were seeing. And what's interesting is this clear relationship that we're seeing between roughness, temperature, and off to on band ratio. And that is because LAMP only looks at the topmost 100 nanometers, as I mentioned, monolayers on the surface. The amount of ice that you need to explain the subdued roughness, the terrain softening, is a lot more than we see with LAMP, and it's probably subsurface. So this is a weird correlation that we were not expecting, but it could imply that there's a relationship between the surface ice and the subsurface ice. So to summarize this part of the talk here, we looked at roughness at two different baselines. We found that at both baselines, the regions of interest of cold traps were smoother than the surrounding regions. We looked at Amundsen. We found that the Amundsen PSR was 35% smoother than its equivalent illuminated area. And we found this correlation between off to on band ratio, roughness, and temperature, which is possibly indicative of the volatile related terrain softening idea that was put forth previously. And it could imply a correlation between the surface ice and subsurface ice. So now the challenging task of summarizing everything I've been talking about in one slide. We investigate the South Pole. We look at LAMP signatures. We find increased porosity within cold traps. We find off to on band ratios that are higher within these areas, and we find that that's consistent with 1.4% H2O. Next, we look at LAMP and diviner signatures. We find that this off to on band ratio is constrained to temperatures of 115 colder. And we develop a way to look at the relative abundance of H2O and H3 and CO2. And then lastly, we look at LOLA roughness and find decreased roughness. So we find smoothing within these cold traps. And we find that it's correlated with LAMP and temperature. And this is, again, indicative possibly of a correlation between the surface and subsurface volatiles. So if you want to learn more, this has all been published in these 3 papers. All of this work was funded by LRO, particularly the LAMP instrument, and also by the Survey IS50 node. So with that, I will take any questions.